Hello and welcome to today's video. In this video, we're going to talk about the LeastSquares method. Now, the idea here is that often in applications, you have a lot of data and you want to find a good functional description of that data. One possibility to do this is to conjecture a correlation. For example, you could conjecture that the data is correlated in a linear way. So one part of the data depends on the other part in a linear way. And you want to determine the right parameters for that linear function. Usually there's a lot more data than necessary to determine those parameters. And determining those parameters would amount to solving a system of equations. Hopefully linear, so that we can apply the methods that we have developed for linear equation systems. However, if you plug in all of your data, then in most cases, you will end up with a system that is infeasible. And that's simply because the correlation might not exactly be modeled by a linear function. So you might have some measurement errors, for example, that this function, of course, does not account for, or the correlation is roughly linear, but not exactly, and you don't really care about having it exactly as long as you get the trend right. So you'd like to have a method of still getting to your parameters without solving that system of linear equations. And of course, one thing you could do is you could take just part of your data, just enough to determine all the parameters, and use that. But then, depending on what part of the data you choose, you'll get a different function. And of course, that's also not something you usually want. So in this chapter here, we're going to develop a method that deals with exactly this situation. We have a system of linear equations that is overdetermined and infeasible. And we want to have a solution, an approximate solution at least, for that system. And we're going to develop a method that does just that using orthogonal projections. This method is called the LeastSquares method. And that's also the title of this chapter here. So we talk about the LeastSquares method here. We'll start with an example to illustrate that problem. Basically, that's the setting that I've just talked about. Let's say you're working for a bank and you want to estimate the effect of the interest rate on credit consumption by consumers. You have a lot of historical data and you want to find out what the correlation or what the parameters of the correlating function are. So let's say a bank wants to estimate the effect of the interest rate on credit consumption. There is historical data available. You just choose to plot that data by doing a plot that contrasts interest rate and consumption. And let's say you get a number of points that seem to suggest there might be at least closely a linear correlation between those two. So historical data suggests a linear correlation, meaning the points Ri and Ci, where Ri is the interest rate, let's say in week I, and Ci is the credit consumption in week I. Let's say those 2 points, or those points here, roughly lie on a line. And approximately, because of course we all know that the interest rate is not the only factor that will influence your credit consumption. So there's a lot of other factors involving this, but you don't want to have those in your model because it would get too detailed and you cannot measure all the effects of these other factors anyway. So why bother with that? I just want to isolate the main factor, and that seems to be the interest rate, and I want to get the approximate trend of that factor rate. Okay, so what you want to do is you want to obtain the right parameters for a linear function that roughly models this correlation here. Okay, so we want to obtain parameters, let's call those alpha and beta, two real numbers, such that a function of the form f of r is alpha times r plus beta is at least a good approximation for the measurements. And of course, good may not be good enough. We want the best possible approximation in a way that we'll define later. We have those measurements here, Ri, Ci. You have, let's say, n points available here. Of course, ideally, f of Ri would be equal to Ci for all n, but that's usually not possible. Then we could just define alpha beta as solutions of a feasible system of linear equations, but usually that's not the case. So usually there are measurement errors or other influences that we don't incorporate into the model, etc., such that this is not the case. Now, if it would be the case, we could of course determine alpha and beta as solutions to a system of linear equations. So if f of Ri would be equal to Ci for all I in n, then alpha and beta satisfy the following system of linear equations. Now the SLE we get here is the following, assuming that R1 and C1 satisfies f of R1 equals C1, and f of R1 is alpha times R1 plus beta, that is then equal to C1. If the same is true for R2 and C2, then we get alpha times R2 plus beta is C2, and so on. That is true for all points Ri, Ci, up to alpha times Rn plus beta is equal to Cn. And that's a linear system in alpha and beta, and it can be translated to Tupelo form, of course. So what we get here is a matrix of the form R1, R2, and so on to Rn. And we have ones, those are for the beta. This we multiply by the vector of unknowns, alpha, beta, and the right-hand side is C1, C2 to Cn. So that's a linear system that's overdetermined because we only need 2 linearly independent equations to solve it, and there's lots more here. So usually that's infeasible, and the question is, how do we deal with that? Right, so the problem here is that is usually an infeasible system. So we want something like an approximate solution. How do we get that? Let's have a look at that situation from a more abstract viewpoint. Here's the general setting that we're going to deal with. So what we have is a matrix and the right-hand side form a system of linear equations, but that is infeasible. That means the right-hand side is not in the column space of the matrix. So we have a matrix A, let's say an M by N matrix, and we have B in R to the M with B not in the column space of A. And that means AX equals B is infeasible. So what we want to do now is we want to find a vector, let's call it B hat, that is in the column space. So AX equals B hat has a solution and close to the vector B in some measurement. So here's the task. We want to find a vector B hat in Rm, where B hat is contained in the column space of A, meaning AX equals B hat is feasible, so we can determine a solution to that system. And that vector needs to be close to B. And what we mean by close is the distance between those two vectors is not too large, and we measure distances usually by using norms. So the norm of B minus B hat is minimized for a given norm. Usually we'll use the Euclidean norm for this, but of course, depending on the situation, some other norm might be more suitable. Now, how do we get that? Well, the idea is we have this vector B that is not in the column space. We have the column space, a vector space spanned by the columns. What's the closest vector in the column space to B? Well, to get the closest vector in a certain vector space to a vector that's not in the space, what you usually do is you compute the orthogonal projection. And that's exactly what we're going to do here. So here's how we solve this situation. To be able to compute that with the methods that we will introduce here is we need a matrix that has full rank. So usually the column rank will be full, right? Usually we have more equations than we need, but we have enough to solve the system uniquely. So let A be a matrix in R to the M by N with the rank of A being N, so full rank. And let B be in R to the M. Furthermore, we'll define B hat as the orthogonal projection of B to the column space of A. So let B hat be the orthogonal projection of B to the column space of A. In other words, B hat is equal to the projection onto the call space of A of B, like this. And then let's see, the theorem says B hat is then the unique right-hand side for which the linear system given by A and the right-hand side has a solution, and such that B minus B hat is minimized. And B hat is the unique right-hand side vector for which the system of linear equations AX equals B hat has a solution and such that B minus B hat is minimal among all such right-hand sides. Okay, so basically what we do here is we have this column space. Let's say this is the column space here in a very simple two-dimensional setting. And we have this right-hand side vector B that is not contained in the column space. What we do is we compute the orthogonal projection of B onto the column space. It would be this vector here, and that's our B hat. We can solve the system of linear equations with B hat, and the distance between those two is minimal, right? That this is this distance here. So this is B hat minus B. Now the second part of the theorem tells us how to solve this projection for the canonical scalar product. And actually that's something that we've discussed already, but to keep it in this theorem so that you can refer to that later on, we'll write it down again. So for the canonical scalar product, and the associated Euclidean norm, B hat can be computed as follows. And again, we've discussed this in the video on orthogonal projections already, so if you don't know how to get these formulas, then please refer to that video. First we need to do is we need to determine the coefficients of that vector B hat. So we determine the unique vector, let's call it x hat, such that A transposed A x hat is equal to A transposed B. Again, this is exactly the formula that comes from this projection. And second, we just set B hat to A times x hat, right? So that gives you the right projection. The vector x hat is then called the least squares solution of our linear system. X hat, and it can also be expressed as A transposed A to the minus 1 times ATB. Remember, if A has full rank, then ATA is invertible, so we can express xhat in this way if we want to. But that's more of theoretical interest. Usually you just use, compute the solution to that linear system to get xhat, and you don't invert the matrix. So this vector is then called the LeastSquares solution of AX equals B, of the original system of linear equations. And the reason for that name is it minimizes the expression B minus B hat. And of course, if it minimizes the norm, then it also minimizes the square of that norm. And we often write the square to avoid the square roots when evaluating that norm. And that is, of course, the same thing as B minus AX hat. And that in turn is the same thing as the sum of all BI minus AI transposed X hat, where this AI transposed is one of the lines of the matrix A, and squared, right? So this goes from I to M, and this is meant to be the ith row of A. And that's where the name comes from, right? You have a number of squares, sum up those squares, and that's where this least squares solution comes from. So that's how the process works. Let's see an easy example first to see how we can apply this. And then in one of the follow-up videos to this one here, we'll see a more complex example, but we then use a computer to compute the solutions to the system of linear equations. So here we'll start with a very simple example. We'd start with a 3 by 2 matrix. That looks like this here. And we'll take the right-hand side B to be minus 1, 2, 2. And we'd like to solve the system of linear equations AX equals B. Now if we try that, let's do that just to illustrate that it won't work. If we try that, we get this tableau. Then we would first subtract row 1 from row 3. That would yield 1, 2, minus 1 here, 0, 1, 2. We just copy the first 2 rows. In the last row, we would get 0, minus 3, and plus 3, like this. And then, of course, we could add 3 times the second row to the third one. And we'd obtain this matrix here. So copy the first 2 rows again. And then the third row is 0, 0, and 3 plus 6, that would be 9. So it would look like this. And as you can see here, this last row clearly indicates there is no solution to that system. The system is infeasible. And that, of course, means B is not contained in the column space of A, right? Otherwise, would be linear combinations of the columns of A that gets you B, and the coefficients of the linear combination would be the right X, the solution that we're looking for. This is not the case. The system is infeasible. So we want to determine a least square solution. How do we do that? Well, remember, we need to determine a solution to the system A transposed AX equals A transposed B. So we first compute A transposed A and A transposed B. So let's see, A transpose A, that is 1, 2, 0, 1, 1 minus 1, that's A transposed. A is 1, 2, 0, 1, 1 minus 1, like this. Now what we will get is a 2 by 2 matrix. The first row is, let's say, 1 plus 1, that's 2. Second row, first column is 2 minus 1, that's a 1. Then we get first row, second column. We get a 2 minus 1, that's a 1 again. And for the last entry, we get 4 plus 1 plus 1, that's a 6. Quick check, by the way, this matrix here, this is always symmetric. So of course your end result should also be symmetric. If it isn't, you messed up somewhere. Yeah, so take a quick look at this end result. It needs to be a symmetric matrix, and in this case it is. So that seems right. A transpose B. Again, let's write down A transposed here. And B was a vector minus 1, 2, 2. And if we multiply that, we get, let's see, minus 1 plus 2, that's plus 1. And minus 2 plus 2 minus 2, that's a minus 2. So here's the system we need to solve. That is 2, 1, 1, 6, and the right-hand side is 1, minus 2. And that's a 2 by 2 system now, so that should have a solution, and even a unique one in this special case, because the rank of A was 2. So, well, how do we get that solution? Let's start by exchanging those rows here to get the 1 as a pivot element. It's a little nicer. And then we subtract 2 times the first row from the second. And let's see, that yields 0. Then 1 minus 12 is minus 11. And 1 plus 4, that's 5. So what we get here is, as our solution x hat, x hat 2 is 5 over minus 11, so that's minus 5 over 11. And x hat 1 is minus 2 minus 6 x hat 2. So let's see, that's minus 2 is minus 22 over 11. Minus times minus, that's a plus. 6 times 5 is 30 over 11. So we get 8 over 11. Right? And that means our least squares solution x hat is 1 over 11, 8 minus 5. Right? So that is the least squares solution to our system. And just to complete that, we can also compute the corresponding b hat. That's simply a x hat. So let's write down a again. And multiply this by 1 over 11 times 8 minus 5. And we get 1 over 11 times, let's see, 8 minus 10, that's minus 2, minus 5, and 8 plus 5, that is 13. So that's the corresponding right-hand side vector compared to our original right-hand side vector, which was, remember, which was minus 1, 2, 2. Right? So that is the vector that is closest to the original and is in the column space of A. Okay, so this here is our original B, well, this is B hat. And again, that minimizes A x hat minus B. right? So xhat does not exactly solve the system, but at least it minimizes the difference here, right? And of course, if B happens to be in the column space, then that method works as well, and it yields an exact solution in that case. Okay, so that completes our introduction to the least squares method. In the upcoming videos, I'm going to show you an application with a few more data points and a few plots so that you can see how this method actually works in practice if it's applied to larger data sets. And we'll also have a look at other function models, not just the linear models. Other functions can be modeled in a similar way here. As usual, I hope I'll see you then.